Tutorial 7, Flight Instruments. This tutorial will cover flight instruments. In order to safely fly any aircraft, a pilot must understand how to interpret and operate the flight instruments. The pilot also needs to be able to recognize associated errors and malfunctions of these instruments. The pitot-static system is a combined system that utilizes the static air pressure and the dynamic pressure due to the motion of the aircraft through the air. These combined pressures are utilized for the operation of the airspeed indicator, ASI, altimeter, and vertical speed indicator, VSI, shown above. The pitot tube is utilized to measure the total combined pressures that are present when an aircraft moves through the air. Static pressure, also known as ambient pressure, is always present whether an aircraft is moving or at rest. It is simply the barometric pressure in the local area. Dynamic pressure is present only when an aircraft is in motion. Therefore, it can be thought of as a pressure due to motion. Wind also generates dynamic pressure. It does not matter if the aircraft is moving through still air at 70 knots or if the aircraft is facing a wind with a speed of 70 knots. The same dynamic pressure is generated. The pitot tube has a small opening at the front which allows the total pressure to enter the pressure chamber. The total pressure is made up of the dynamic pressure plus static pressure. The one instrument that utilizes the pitot tube is the ASI. The total pressure is transmitted to the ASI from the pitot tube's pressure chamber via a small tube. The static pressure is also delivered to the opposite side of the ASI, which serves to cancel out the two static pressures, thereby leaving the dynamic pressure to be indicated on the instrument. When the dynamic pressure changes, the ASI shows either increase or decrease, corresponding to the direction of change. The two remaining instruments, altimeter and VSI, utilize only the static pressure, which is derived from the static port. The static chamber is vented through small holes to the free, undisturbed air on the sides of the aircraft. As the atmospheric pressure changes, the pressure is able to move freely in and out of the instruments through the small lines which connect the instruments into the static system. An alternate static source is provided in some aircraft to provide static pressure should the primary static source become blocked. The alternate static source is normally found inside the flight deck. The altimeter is an instrument that measures the height of an aircraft above a given pressure level. Since the altimeter is the only instrument that is capable of indicating altitude, this is one of the most vital instruments installed in the aircraft. To use the altimeter effectively, the pilot must understand the operation of the instrument, as well as the errors associated with the altimeter and how each affect the indication. A stack of sealed aneroid wafers comprise the main component of the altimeter. An aneroid wafer is a sealed wafer that is evacuated to an internal pressure of 29.92 inches of mercury. These wafers are free to expand and contract with changes to the static pressure. A higher static pressure presses down on the wafers and causes them to collapse. A lower static pressure allows the wafers to expand. A mechanical linkage connects the wafer movement to the needles on the indicator face, which translates compression of the wafers into a decrease in altitude and translates an expansion of the wafers into an increase in altitude. The dial of a typical altimeter is graduated with numbers arranged clockwise from 0 to 9. Movement of the aneroid element is transmitted through gears to the three hands that indicate altitude. The shortest hand indicates altitude in tens of thousands of feet, the intermediate hand in thousands of feet, and the longest hand in hundreds of feet. Adjustments for non-standard pressures are accomplished by setting the corrected pressure into a barometric scale located on the face of the altimeter. It is easy to maintain a consistent height above ground if the barometric pressure and temperature remain constant, but this is rarely the case. The pressure temperature can change between takeoff and landing even on a local flight. If these changes are not taken into consideration, flight becomes dangerous. If altimeters could not be adjusted for non-standard pressure, a hazardous situation could occur. For example, if an aircraft is flown from a high-pressure area to a low-pressure area without adjusting the altimeter, a constant altitude will be displayed, but the actual height of the aircraft above the ground would be lower than the indicated altitude. There is an old aviation axiom, going from a high to a low, look out below. Conversely, if an aircraft is flown from a low-pressure area to a high-pressure area without an adjustment of the altimeter, the actual altitude of the aircraft is higher than the indicated altitude. Once in flight, it is important to frequently obtain current altimeter settings en route to ensure terrain and obstruction clearance. Adjustments to compensate for non-standard pressure do not compensate for non-standard temperature. Since cold air is denser than warm air, when operating in temperatures that are colder than standard, the altitude is lower than the altimeter indication as shown above. A variation of the memory aid used for pressure can be employed. From hot to cold, look out below. Extremely cold temperatures will also affect altimeter indications. The above image, which was derived from ICAO formulas, indicates how much error can exist when the temperature is extremely cold. Look at the chart using a temperature of -10 degrees Celsius, and the aircraft altitude is 1,000 feet above the airport elevation. The chart shows that the reported current altimeter setting may place the aircraft as much as 100 feet below the altitude indicated by the altimeter. Most altimeters are equipped with a barometric pressure setting window, or Colesman window, providing a means to adjust the altimeter. A knob is located at the bottom of the instrument for this adjustment. To adjust the altimeter for variation in atmospheric pressure, the pressure scale in the altimeter setting window, calibrated in inches of mercury, Hg, and or millibars, MB, is adjusted to match the given altimeter setting. Altimeter setting is defined as station pressure reduced to sea level, but an altimeter setting is accurate only in the vicinity of the reporting station. Therefore, the altimeter must be adjusted as the flight progresses from one station to the next. To illustrate the use of the altimeter setting system, follow a flight from Dallas Love Field, Texas, to Abilene Municipal Airport, Texas, via Mineral Wells. Before taking off from Love Field, the pilot receives a current altimeter setting of 29.85 inches from the control tower, or ATIS, and sets this value in the altimeter setting window. When over Mineral Wells, assume the pilot receives a current altimeter setting of 29.94 inches and sets this in the altimeter window. Before entering the traffic pattern at Abilene Municipal Airport, a new altimeter setting of 29.69 inches is received from the Abilene control tower and set in the altimeter setting window. However, assume the pilot did not adjust the altimeter at Abilene to the current setting and continued using the Mineral Wells setting of 29.94 inches. When entering the Abilene traffic pattern at an indicated altitude of 2,600 feet, the aircraft would be approximately 250 feet below the proper traffic pattern altitude. Upon landing, the altimeter would indicate approximately 250 feet higher than the field elevation. Altitude in itself is a relevant term only when it is specifically stated to which type of altitude a pilot is referring. Normally, when the term altitude is used, it is referring to altitude above sea level, since this is the altitude which is used to depict obstacles and airspace, as well as to separate air traffic. Altitude is vertical distance above some point or level used as a reference. There are as many kinds of altitude as there are reference levels from which altitude is measured, and each may be used for specific reasons. Pilots are mainly concerned with 5 types of altitudes. 1. Indicated altitude, read directly from the altimeter, uncorrected, when it is set to the current altimeter setting. 2. True altitude, the vertical distance of the aircraft above sea level, the actual altitude. It is often expressed as feet above mean sea level, MSL. Airport, terrain, and obstacle elevations on aeronautical charts are true altitudes. 3. Absolute altitude. The vertical distance of an aircraft above the terrain or above ground level, AGL. 4. Pressure altitude. The altitude indicated when the altimeter setting window, barometric scale, is adjusted to 29.92 inches. Pressure altitude is used to compute density altitude, true airspeed, TAS, and other performance data. 5. Density altitude. Pressure altitude corrected for variations from standard temperature. When conditions are standard, pressure altitude and density altitude are the same. This is an important altitude because it is directly related to the aircraft's performance. Prior to each flight, a pilot should examine the altimeter for proper indications in order to verify its validity. To determine the condition of an altimeter, set the barometric scale to the current reported altimeter setting transmitted by the local automated flight service station, AFSS, or any other reliable source, such as ATIS, AWOS, or ASOS. The altimeter pointers should indicate the surveyed field elevation of the airport. If the indication is off more than 75 feet from the surveyed field elevation, the instrument should be referred to a certificated instrument repair station for recalibration. The VSI indicates whether the aircraft is climbing, descending, or in level flight. The rate of climb or descent is indicated in feet per minute, FPM. If properly calibrated, the VSI indicates 0 in level flight. The inside of the diaphragm is connected directly to the static line of the pitot-static system. The area outside the diaphragm, which is inside the instrument case, is also connected to the static line, but through a restricted orifice, calibrated leak. Both the diaphragm and the case receive air from the static line at existing atmospheric pressure. The diaphragm receives unrestricted air, while the case receives the static pressure via the metered leak. When the aircraft is on the ground or in level flight, the pressures inside the diaphragm and the instrument case are equal, and the pointer is at 0 indication. When the aircraft climbs or descends, the pressure inside the diaphragm changes immediately, but due to the metering action of the restricted passage, the case pressure remains higher or lower for a short time, causing the diaphragm to contract or expand. This causes a pressure differential that is indicated on the instrument needle as a climb or descent. As part of a pre-flight check, proper operation of the VSI must be established. Make sure the VSI indicates near 0 prior to leaving the ramp area and again just before takeoff. If the VSI indicates anything other than 0, that indication can be referenced as the 0 mark. Normally, if the needle is not exactly 0, it is only slightly above or below the 0 line. After takeoff, the VSI should trend upward to indicate a positive rate of climb, and then, once a stabilized climb is established, a rate of climb can be referenced. The ASI, shown above, is a sensitive differential pressure gauge which measures and promptly indicates the difference between pitot, impact dynamic pressure, and static pressure. These two pressures are equal when the aircraft is parked on the ground in calm air. When the aircraft moves through the air, the pressure on the pitot line becomes greater than the pressure in the static lines. This difference in pressure is registered by the airspeed pointer on the face of the instrument, which is calibrated in miles per hour, knots, nautical miles per hour, or both. The ASI introduces the static pressure into the airspeed case, while the pitot pressure, dynamic, is introduced into the diaphragm. The dynamic pressure expands or contracts one side of the diaphragm, which is attached to an indicating system. Just as in altitudes, there are multiple types of airspeeds. Pilots need to be very familiar with each type. 1. Indicated airspeed, IAS. The direct instrument reading obtained from the ASI, uncorrected for variations in atmospheric density, installation error, or instrument error. Takeoff, landing, and stall speeds listed in the AFM POH are IAS and do not normally vary with altitude or temperature. 2. Calibrated airspeed, CAS. IAS corrected for installation error and instrument error. Although manufacturers attempt to keep airspeed errors to a minimum, it is not possible to eliminate all errors throughout the airspeed operating range. At certain airspeeds and with certain flap settings, the installation and instrument errors may total several knots. In the cruising and higher airspeed ranges, IAS and CAS are approximately the same. Refer to the airspeed calibration chart to correct for possible airspeed errors. 3. True airspeed, TAS. CAS corrected for altitude and non-standard temperature. A pilot can find TAS by two methods. The most accurate method is to use a flight computer. With this method, the CAS is corrected for temperature and pressure variation by using the airspeed correction scale on the computer. A second method, which is a rule of thumb, provides the approximate TAS. Simply add 2% to the CAS for each 1,000 feet of altitude. The TAS is the speed which is used for flight planning and is used when filing a flight plan. 4. Ground speed, GS. The actual speed of the airplane over the ground. It is TAS adjusted for wind. GS decreases with a headwind and increases with a tailwind. Aircraft weighing 12,500 pounds or less, manufactured after 1945 and certificated by the FAA, are required to have ASIs marked in accordance with a standard color-coded marking system. This system of color-coded markings enables a pilot to determine at a glance certain airspeed limitations that are important to the safe operation of the aircraft. As shown in above, ASIs on single-engine small aircraft include the following standard color-coded markings. 1. White arc, commonly referred to as the flap operating range, since its lower limit represents the full flap stall speed and its upper limit provides the maximum flap speed. 2. Lower limit of the white arc, VSO, the stalling speed or the minimum steady flight speed in the landing configuration. 3. Upper limit of the white arc, VFE, the maximum speed with the flaps extended. 4. Green arc, the normal operating range of the aircraft. Most flying occurs within this range. 5. Lower limit of the green arc, VS1, the stalling speed or the minimum steady flight speed obtained in a specified configuration. For most aircraft, this is the power-off stall speed at the maximum takeoff weight in the clean configuration, gear up if retractable, and flaps up. 6. Upper limit of green arc, VNO, the maximum structural cruising speed. Do not exceed this speed except in smooth air. 7. Yellow arc, caution range. Fly within this range only in smooth air and then only with caution. 8. Red line, VNE, never exceed speed. Operating above this speed is prohibited since it may result in damage or structural failure. Some important airspeed limitations are not marked on the face of the ASI, but are found on placards and in the AFM POH. These airspeeds include 1. Design maneuvering speed, VA, the maximum speed at which the structural design's limit load can be imposed, either by gusts or full deflection of the control surface without causing structural damage. 2. Best angle of climb speed, VX, the airspeed at which an aircraft gains the greatest amount of altitude in a given distance. 3. Best rate of climb speed, VY, the airspeed that provides the most altitude gain in a given period of time. Prior to takeoff, the ASI should read 0. However, if there is a strong wind blowing directly into the pitot tube, the ASI may read higher than 0. When beginning the takeoff, make sure the airspeed is increasing at an appropriate rate. We hope you learned a lot. Please help us spread the word about Pilot Training System, and we look forward to further servicing your flight training needs.